This is a tutorial video showing you one method you can use to collect data that will allow you to calculate the rate of a chemical reaction. In this video, we'll look at how to measure the rate of a reaction that becomes turbid, which is one half of the GCSE Chemistry Required Practical for AQA. By now, you're hopefully aware that the rate of a chemical reaction is a way of describing its speed. Now, ordinarily, when we're trying to calculate the rate of a reaction, we use a formula that is something like the reactant used or the product made divided by the time taken. And that's very useful for reactions that maybe give off a gas. So they release some gas that we can capture and we could measure a volume, and also their mass changes as that gas is lost to the environment. But that's not very useful for all reactions. So in this video, we're going to look at a reaction that becomes turbid. The required practical for AQA GCSE Chemistry Unit 6 has two parts to it. Firstly, you investigate a reaction that loses gas, which you can collect using either a gas syringe or collecting gas over water. And then secondly, you need to examine a method that uses turbidity. So the classic example for this is the reaction of hydrochloric acid and sodium thiosulfate, which turns cloudy as a yellow sulfur precipitate is formed. You aren't expected to remember all the details and the symbol equation for this reaction, but to be honest, it's the only chemical reaction I've seen studied at GCSE which does become turbid, so it's very, very likely that a question will be put in this context. They could ask you why this reaction goes cloudy, and the key thing to note is this state symbol here around sulfur. You can see there's a little S in brackets, and that tells you that it's a solid. Now, when a solid is being formed out of solutions, we call that a precipitate, and that is what's going to make the solution go cloudy, just like when you blow into lime water and it turns milky white, because there you're forming a calcium carbonate precipitate. For any investigation in GCSE chemistry, and to be honest, any science at all, it's really important before you start to identify your variables so that you're only changing one thing. According to the required practical, you need to change the concentration, but it doesn't actually specify the concentration of what. In the video I'm going to show you of me doing the practical, I changed the concentration of the sodium thiosulfate, and this is purely because it's a much larger volume, and therefore for my year 9 pupils it's easier for them to handle changing the concentration of that. But actually a lot of protocols for this practical talk about changing the concentration of the acid instead. Whichever one you do, it's totally fine, but it's important that you're only changing the concentration of one of them. So if we're going to change the concentration of sodium thiosulfate, then the concentration of the hydrochloric acid would be a control variable, or vice versa. The dependent variable is the thing that I'm observing to see how it's affected. So here it's the rate of reaction. But I can't actually measure that directly, so what I'm really going to be measuring is the time taken for a cross on a piece of paper to disappear, or at least for me to not be able to see it anymore. And then I'm going to use that to calculate the rate. My other control variables need to include the volume of the sodium thiosulfate, and remember, we cannot use the word amount because that would not be accurate. You need to be talking about volume. Likewise, the volume of hydrochloric acid. And you could also talk about controlling the temperature of this reaction, because the temperature will have an impact. However, if you say that you're going to control the temperature, that would describe a situation where you maybe had a hot water bath, so you were actively doing something to keep the temperature the same. Doing it at room temperature every time is not controlling the temperature. In this example, I'm only going to test 2 concentrations of sodium thiosulfate, although ordinarily you might make up maybe 5 different concentrations to test, but I don't have that many hands. So you can see here I've got my hydrochloric acid and sodium thiosulfate. You aren't supposed to remember the names of those chemicals, but realistically that's what the question is likely to be about. And so I need to start off by making it my different concentrations. So you can see here I've got 50 centimetres cubed of sodium thiosulfate in the measuring cylinder, and then over on this side I've only got 10 centimetres cubed. Now I need the volume to be the same of the two of those, so I'm now going to top up this second measuring cylinder with water so that the total volume is also 50 centimetres cubed. Because the total volume of the solutions, that's going to be one of my control variables, and therefore I need it to be the same for every experiment. So I'm making my lower concentrations of sodium thiosulfate by diluting my higher concentration, and I'm doing this using a measuring cylinder so that I can see exactly how much water I've added and therefore calculate a new concentration. So both of those measuring cylinders are going to be decanted into a conical flask, and we use a conical flask just because it's going to mean that any splashing doesn't actually get out of the reaction vessel like it might if we were using a beaker. So both of those are going to go into there, and the reaction won't start, and it won't start going cloudy until I add the acid. So that's the very last thing that I'm going to do. But before I add that acid, I'm going to put both of these on a cross that I've drawn on a piece of paper. Now, in an ideal world, I would do them on the same cross, but here I'm trying to do them both at the same time just so that you can see the difference between them. So that sodium thiosulfate, either concentrated or dilute, is on that cross. And then what I'm going to try and do, more or less simultaneously with limited success, is add the acid to these and start the stop clock. So obviously I can't actually add them at exactly the same time, but you're going to get the general idea anyway. So now that those have been added together, this reaction is going to start, and that solid sulfur precipitate that we talked about is going to be produced. And so because you're producing that solid sulfur within the aqueous solution, that's going to make the solution start to go turbid or start to go cloudy. And what I'm waiting for is the point where, looking down from on high, I can no longer see that cross that I've drawn on the piece of paper. Now, obviously, there's a bit of a problem with this, that this is all down to my human judgment and where I think I can't see it anymore, which is going to be affected by how good my eyes are. So a better way to run this experiment would actually be to use a light sensor that I could put underneath the beaker, underneath the conical flask, sorry, and I could see in terms of numbers when is less light getting through, and judge the end of the reaction that way. So here you can see my left-hand one, my more concentrated solution, is starting to get cloudier and cloudier, and it's getting harder and harder to see that cross due to the turbidity, to the point where eventually I think it's about to disappear. But as we say, this is very much down to human judgment, and that's one of the errors that we're going to see in this experiment. Once you've completed the investigation for each of your 5 concentrations, it's normal to then repeat the investigation twice more so that you have 3 sets of data per concentration. But why do we do this? Those pieces of data can be used to calculate a mean for each concentration. Remember, when you're describing a required practical or something like that, you get credit for saying repeat the investigation and calculate a mean. You don't get credit for just saying repeat it. But why do we do this? Well, it's to reduce random error. So this is normal fluctuation around the mean that happens just because of things like changing temperature in the room. And by taking a number of repeat readings and calculating a mean, we're going to reduce this random error. To analyse the data with this practical, I'm going to list my concentrations with the times alongside. Remember that your units should only be in the header of a table. You shouldn't be writing seconds or whatever down in the main body of the table. I'm then going to use those times to calculate a rate. You can see here that the units for time are seconds and the units for rate are seconds to the -1. That means the same thing as 1 divided by seconds. So all we're doing here is taking our time, say 350 seconds, and doing 1 divided by that 350 to get our rates. Now, that rate data may have looked pretty big and scary, but it definitely gives us an advantage when it comes to plotting a graph. So when you plot the graph, your independent variable always goes on the x-axis. So I've got concentration of sodium thiosulfate at the bottom. And again, you can see that I've got my units there in the axis legend. And then I've got rate of reaction up my y-axis. And the advantage of plotting concentration against rate rather than concentration against time is that actually for this experiment, I get this lovely straight line graph. And that makes it really easy for me to make predictions about what the rate would be at a different concentration, say 0.05. Thank you very much for watching, and I hope you found this a useful tutorial for how to calculate the rate of a reaction based on a reaction measuring turbidity. Don't forget to also watch parts 1 and 2, where we examine measuring rates of reaction using volume changes and mass changes.